So for reviewing chapter 5 and 7, I'm going to solve some question on chapter 5, which is, and this question is at the end of exercise 5. So these are on mass, conservation of mass, momentum, and energy. So let's first start this question. We have an empty tank that the weight on a scale is 450 Newton when it's empty. And then this pipe is going to have some inflow of water to the tank, and also these two pipe, there are some water coming out of the tank. So it's, if we consider a steady state, then the tank, when it has the water in some level, the volume of the tank going to be 50 liters of water. And now we are trying to find, and also it said that the tank is not moving horizontally. So now we are trying to find the values for the forces in case that don't allow the tank to move. So let to move horizontally. So let's move. Let's see how we can solve it. So always when you want to solve the equations, first you need to write down whatever you have, and then whatever the question asks for, right? So let's write down what you have. So you have the, oops, sorry. So you have the weight of tank, right? So you have the weight of tank, which is 450 newtons. You have the volume of tank, which is 50 liter. You have V2, which is 4 meter per second. So you have D1, D2, and D3, meaning that you have A1, A2, and A3, right? And what else you have? Yeah, these are the things that you have, right? And now you are trying to find the scale reading, right? So scale reading. Now let's write down also our assumption. So in the question, it said that assume a steady state. Also, we can say that it's one-dimensional flow. We have constant properties. And also, it's all at the atmosphere, all of the pressure at the atmosphere. We can just assume that the atmosphere pressure acts everywhere. So these are the assumptions that we have, and now we know that we need to use conservation of mass and momentum. So we need to use conservation of mass because we have inflow and outflow, and momentum because we are trying to find the scale reading, means it depends on the forces, right? So this case we need to have the momentum. So for solving conservation of mass and momentum, there were some steps and procedure that you need to follow to solving the question. The first one was to draw your control volume. So I have inflow here, outflow here, and here. So somehow I need to draw the control volume to pass these openings. So now I have my CV. Now I need to fix and assign my coordinate system, my X, V, and Z. So I'm going to assume this is X and this is Y direction. And so we fix X, Y, and Z. We draw the control volume. And for the mass flow, for the momentum, we need also to show all of the forces on the control volume, right? So we have the weight of the tank when it's empty. We have also the weight of water in the tank. So also we have the reaction force. So if I say that this is Ry, this one going to be Rx, and then I'm not going to also show the P atmosphere because it's going to be cancelled in all of the directions. So we don't need to show that one. Now let's write down the conservation of mass. So oh my God. So conservation of mass. So one flow is coming in and two flow going out. So if I just write down the section, it's section 1, section 2, and then section 3, right? Now let's write down the conservation of mass. So one flow is coming in, two flow going out. So just simply m dot 1 equal to m dot 2 plus m dot 3. And because of a steady state, you don't have the first term in the conservation of mass. So this is how it's going to be simplified. Now and we know that m dot is equal to rho VA, right? So rho VA, let's write it down for all of the sections. So instead of m dot 1, I'm going to write down rho 1 V1, and A1 is pi 4 D1 squared. And then we have m dot 2, which is rho 2 V2 pi 4 D2 squared. And then we have rho 3 for m dot 3 V3 times pi 4 D3 squared. So these are going to be cancelled out, this pi 4, and also the density, because we have the same fluid, so the same density. And also we can say that in the assumption we have constant properties, so they are going to be cancelled out. Now we know D1, 2, we don't know V1, we know, do we know V2? Yes, we know V2, we know D2, we don't know V3, and we know D3. So one equation, two unknown. So we need another equation. So let's go and solve it with conservation of momentum. So for conservation of momentum, we know that the formula is sigma of F of the control volume equal to d dt, the integral over control volume of V rho dV plus the integral over the control surface of V rho V dot n dA. And we know that this is n dot, and the sign depends if its outflow is positive and if its inflow it's negative, right? And the V is simply the velocity, and the sign it depends on the direction of the velocity. Now let's simplify that. So we know that we have a steady state. So the first term here is going to be 0, right? And now let's write it down for x direction. So for x direction, we know that, okay, for x direction, we have, what is the forces that we have in x direction? So we only have Rx, and it's positive because it's in positive direction of x. the coordinate system X, and then we have, so let's write down the V, rho V and dA for all of the sections, right? So for all of the sections, so for section 1, we don't have it in X direction, so there is no need to write it down. So we have V2 and V3 in X direction. So let's write down V m dot V2 m dot 2, right? Let's see what is the signs for them. So m dot 2 is going out, so it's going to be positive, right? And V2, it's in this direction, which is opposite of the positive x direction, so we have a negative sign here. And then we have V3 m dot 3, and let's look at the signs. So V3 is in this direction, right? It's here, right here, and it's positive with the x direction, so it has a positive sign. And then m dot 3 is outflow, so it's coming out of the section 3, so it's going to be positive again, right? So this is what we have. Now if we look at the question, it said that the tank doesn't move horizontally, so it means that Rx going to be 0. So from here, if we just rearrange it, we have m dot 2 v2 equal to m dot, this is equal, okay, we have m dot 3 v3, right? And now let's put m dot 3 as rho 2 v2 and a2, which is pi 4 d2 squared times the velocity, which is right here. And then we have m dot 3, which is rho 3 v3 pi 4 d3 squared, and then v3, right? Now from here, if we just simplify that, you're going to get v2 squared d2 squared equal to v3 squared d3 squared. And from here, if you just put the diameters and the velocity of 2, we are going to get the V3 as 2.86 meter per second. So now this is the V3 that we found. And also we have this formula right here that we just found with the conservation of mass. Now we know what is the, now we find it, right? So we find that one, now we can find V1 as the. So if we solve that one for V1, we are going to get, so let me just name this equation as equation 1. So if I use the equation 1, if we substitute V2 in equation 1, substitute in equation 1, then from that we are going to get V1 as 9.61 meter per second, right? Now we still didn't get the answer for a scale reading, so let's write down the conservation of momentum in y direction. So in y direction, so conservation of momentum in y direction. So in y direction, we have Ry, which is positive. We have the V of tank. We have the V of the weight of the water, which we also can say that gamma of water times the volume of the tank. Then in this case, we can get the weight of the water. And then if we look at the right hand side of the equation of momentum from here, we only have m dot 1, right? So if we use that one, then we have v1 and m dot 1 here, and m dot 1 is inflow, so we have a minus sign here, and also we have a positive sign for, sorry, negative sign for v1, because v1 is going to have the direction of v1 is to the from top to the bottom, so it's going to have a negative sign here. So we have a negative sign here, and now let's put all of the values that we have. So we have now we are trying to find Ry, right? We have V tank, we have gamma of water, we have the volume of the tank, we have V1, we just find it here, right? And then also we have m dot 1 because we know V1. So from here, I'm just writing down Ry, and instead of V of tank, we know it's 450 Newton plus, and the gamma of water is 9800 Newton per meter cubic. We have, and also this is the volume of the tank, right? And also we need to write down this one, minus to minus is going to be positive, so we have positive, and V1 is 9.6 1 meter per second, and we can find m dot 1 by writing down rho v1 a1, and we know all of them. So from here Ry is going to be 1121 Newton, and because it's positive, it means that it's going to be upward, right? So then it means that the, let me see the direction that, yeah, we also got it at the upward, so, and it's positive, right? A positive, so it means that the direction that we guessed was right. So for the next question, so I'm going to stop this video and solving the next question on the other video.